the first liquid level film, or indeed level film, was about hydrostatic devices. And hydrostatic devices, they all rely on finding the relation rho g h in some manner, and then calculating the height h. If we then know the cross-sectional area of the tank, then we can calculate the volume of the tank, which is the idea. But they all have the drawback that any change in the temperature will cause a shift in the gravity, and the specific gravity rho, and therefore will affect the reading. Also, they have to be calibrated for the contents of the tank. So each time you shift the contents of the tank to another liquid or another solid, then you have to calibrate the device again. And also, if you have an airtight chamber, you have to know the pressure that is over the tank, because that will influence the overall pressure that you measure here. For example, if I apply a very high pressure on top here, that jet that comes out of the bottom here would have an increased power. Other devices that do not depend on the gravity, for example a float gauge. A float gauge is simply something that floats, like here, or here, the white ball here, and that floats on top of the liquid. So that will measure the true top of the liquid in a very simple manner, which is also low cost, but it has a very short lifetime, because you have mechanical parts that will indeed influence the lifetime of the device. So every time you have moving parts, that reduces the lifetime. It's also subject to growth. If you, for example, use this in salt water, you will have marine growth on the device itself. Load cell is a good device for medium, small or small sized tanks, where you actually measure the mass of the tank itself, and you can do that outside the tank, so you don't need to be in contact with the contents of the tank at all. But again, it's not very convenient for very large tanks, so therefore it's something that you have to be careful about. But it can measure solids like grain, sand, pellets, and so on. Capacitive measurement principle, you have two different principles there, and the idea is that you have to know whether your liquid is conductive or not. Conductive means that it will carry electric current. For example, salt water will carry a current very, very well, because it has ions inside it. While non-conductive liquids could, for example, be clean oil. Oils will not carry an electric current, and therefore is an insulator. The two principles differ in that the first, for the conductive liquid, you attach for a voltage here, and then you attach another voltage here. So you apply, and there's a voltage drop between the tank wall and the core of the meter. Now, when you have a conductive liquid, the voltage you apply here will be found again here. Since the liquid will carry the voltage across to the wall of the rod. The rod here is covered in a red stuff, which is an insulator, for example plastic. So indeed, what I have here is a capacitor that is this large. So it's as large as the height of the liquid. So if I were to draw it symbolically, the capacitor here would be this large. Now if the liquid level drops to down here, the capacitor will now be this large. And since the capacitive the capacitance of a capacitor, C equals epsilon times A over distance. Epsilon is the insulator between the two areas, which in this case is the red coating on the bar in the middle. The area is defined by the plates themselves. So this is a small area here and a large area here. And the D is the thickness of the insulator. So the capacitance is a function of the area, which indeed is a function of the height of the liquid. And hence we can find the volume. Going down to the non-conductive liquids, well then, since the liquid doesn't, there's no current flowing in the liquid, what happens here is that I have a capacitor like this, and what really changes is the dielectric between the two. So the dielectric here will shift upwards and cover more of the area between them. So the epsilon is a function of the liquid height. And since C equals epsilon A over D, that means that capacitance is a function of the liquid height. Time of flight sensors measure the time it takes for a wave to go down and be reflected from the surface and come up again. You can do that in many ways. Sound waves, for example acoustic, use ultrasonic waves that travel down until it meets the surface and then reflects back. You can also use radio waves, then it will be a radar. Radar come in two forms. You have something called a guided radar, where you have a rod which the radio waves will follow, and that is particularly useful if you have elements in a tank that may disturb the wave train that goes to the surface and back up. For example, if you have ladders inside the tank, if you have piping, for example a cooler here, or something, then you need to have a rod which the radar waves will follow. But if you don't have anything like that, you might use a radar that looks like this, that will send radio waves to the surface and they reflect up. And what a detector does, either it's radio waves or audio waves, sound waves, the detector here will measure the time the wave uses back and forth and use that to calculate the distance to the surface. Nucleonic depend on a different principle, that is how much of the gamma rays that are sent through the medium, how much of them are absorbed. And the absorption is dependent on the liquid density. So if I send a gamma ray here, from here and in a section like this, this will have very low absorption, this will have more absorption, and if I fill the tank up here, even this ray will have a lot of absorption with it. And the rod here measures the amount of absorbed gamma rays. Of course, gamma rays, they are dangerous. You don't want to be in contact with gamma rays. So therefore the amount of gamma rays that escape from this measurement setup is very low. And indeed the gamma sources are usually very weak, so it doesn't pose any danger to those that are close to the tank. Some of these detectors, for example the one here in this figure, has a setup where you have one rod here which has gamma sources, and then another rod where you have gamma detectors. So if you fill this with a liquid, they detect which of these detector source pairs that are covered in liquid and which are not. Well, the good thing here is that these can actually distinguish a multi-phase tank. That means that it can distinguish, for example, in a oil separation tank, you have gas on top, then comes a layer of foam, then comes a layer of oil, then comes a layer of emulgates, which is a mix of oil and water, then comes water, and in the very bottom you will have sand build up. So the detector here will detect everything within the range of the tank, which is unique for that measurement principle.